All right, today we're cracking a code that organizes literally everything you can see and touch. We're talking about the periodic table. And trust me, by the end of this, you're not going to see it as just some chart on a classroom wall, but as a truly beautiful map of the entire universe. So let's get into it.
I mean, seriously, just think about that for a second. What if you had a guide that could tell you exactly how all the building blocks of matter are going to behave? The stuff that makes up stars, planets, and even you. Well, that's pretty much what the periodic table is. It's the ultimate cheat sheet for chemistry.
So let's start by thinking of it in a new way. Forget the classroom for a second. Let's think of this thing as a map. Not a map of places, but a map of the fundamental ingredients of everything. Now, this isn't just some random jumble of elements. No. The real magic, the absolute genius of it, is in its structure. The way the elements are laid out in these specific rows and columns tells us not just what they are, but it actually predicts how they're going to act. You could call it a map of chemical personalities. Okay, so to really get how this whole map works, we've got to zoom in. I mean, way in. We need to look at the single tiny building block that this entire chart is based on, the atom. To make this easy, let's just grab one element and put it under the microscope. How about lithium, element number 3? If we can figure out what makes this one little tile tick, we'll basically unlock the logic for the whole table. First thing you notice is that big number at the top, the atomic number. For lithium, it's 3. This is like the atom's social security number, its unique fingerprint. It tells us that lithium has exactly 3 protons in its core. Nothing else has 3. It's what makes lithium, well, lithium. Next up, you've got the mass number. For lithium, that's about 7. This is basically how much the atom weighs. It's the grand total of the heavy particles sitting in the center, the protons plus the neutrons. So if we know it has 3 protons and the total mass is 7, well, a little quick math tells you it must have 4 neutrons, right? So you've got these 3 key players making up every atom. In the center, in what's called the nucleus, you have your protons. They've got a positive charge. And packed in there with them are the neutrons, which, you guessed it, are neutral. Then zipping around that nucleus, you've got the electrons, and they're negative. Now, this is absolutely crucial. In a normal, stable atom, the universe loves balance. It wants to be neutral. So that means for every single positive proton in the middle, there has to be a negative electron orbiting it to cancel out that charge. For our lithium atom, that means 3 positive protons requires, 3 negative electrons. Okay, so let's put all those pieces together for our lithium atom. What do we have? We've got a nucleus, right in the heart, with 3 protons and 4 neutrons. And then, circling around that core are 3 electrons, perfectly balancing out the charge. Boom, that's it. That's the complete blueprint for one single atom of lithium. But hang on, where exactly are those 3 electrons hanging out? It's not just a chaotic swarm. Nope, they're super organized in a very specific and really important way. You can think of it as a kind of cosmic shell game. This whole idea got a huge boost from a Danish physicist named Niels Bohr way back in 1913. He figured out that electrons don't just go wherever they want. They're stuck in these distinct energy levels, or shells, kind of like different lanes on a highway circling the nucleus. And the rules for this game are actually super simple. The first shell, the one closest to the center, can only hold 2 electrons, max. Once that one's full, you start filling up the next one out, and that one can hold up to 8. The third shell, same deal. It also holds 8. And here's the key. They always fill up from the inside out. All right, now that we've got the blueprint for a single atom down, we can zoom back out to the big picture. Let's look at the whole table again and see how this one simple idea creates these amazing, predictable patterns. So what you want to do is look at the vertical columns, the up and down ones. Officially, they're called groups, but honestly, it's way more helpful to think of them as chemical families. Because just like a real family, all the elements in one column share these really important traits. They act alike. Let's just take the very first column, group 1. These are the alkali metals. And check out their melting points. You've got lithium at 180 degrees Celsius. Then you go down one spot to sodium, it drops to 98. Go down one more to potassium, and it's all the way down to 63. You see that? There's a clear pattern emerging here. Yeah, when you see it as a chart like this, the trend is just impossible to ignore, right? As you move down that family, the melting point just keeps on dropping, step by step. This is not random. It's a huge clue that something fundamental is connecting them all.
So what is the secret? What's the family secret here? It all comes back to the electrons, specifically the ones in that outermost shell. And here it is. Lithium, sodium, potassium, all of them have exactly one electron in their outer shell. Just one. That single lonely electron defines their whole personality.
See, atoms have one main goal in life, to have a full outer shell. That's when they're stable and happy. So the elements in group 1 with that one lonely electron, they're givers. They are desperate to get rid of that one electron to become stable. Now compare that to a family on the other side of the table, group 7, the halogens. They're the total opposite. They're takers. They have 7 outer electrons, so they're just 1 electron away from having a perfect full shell. And this is what sets up all of chemistry, really. You've got an element like lithium over here, practically begging to give away its extra electron. And then you have an element like fluorine over there, with this perfect empty parking spot, just waiting to be filled. You put them together, and you get a powerful and, often pretty explosive chemical reaction. And then you have group 8, the noble gases. These are the cool kids of the periodic table. They're perfectly content. Why? Because their outer electron shell is already completely full. They don't need to give electrons, they don't need to take electrons, they've already reached that stable, happy state. So they're super unreactive.
So, you can start to see the beautiful logic of it all, right? The entire table is organized by these repeating patterns, these periodic patterns, in how the electrons are arranged. And that arrangement is what determines everything about how an element behaves. So, what are the big things to remember here? First, an atom's identity comes from its protons, but its personality comes from its electrons. Second, those columns aren't random. They're families, bonded together by having the same number of outer electrons. And that leads to the final point. The periodic table isn't just a list, it's a predictive map of all the matter in the universe.
But here's the truly mind-blowing part. These patterns are so reliable, so perfect, that scientists have used them to predict the existence and even the properties of elements before they were ever discovered. Think about that. This code doesn't just explain the world we already know, it gives us a blueprint for parts of the universe we haven't even found yet. Which just leaves you wondering, what other secrets is it still waiting to tell us?